Alrighty, folks, so welcome to the first lesson of Physics 30. So in these video lessons, what I'll do is I'll work through the notes that I've given you access to in the Google Classroom and also in the agenda. Okay, and I'll solve the examples, I'll talk through the important concepts and all that stuff. Physics definitely is something that's not best learned just by sitting back and listening. So I really do recommend that you get some paper, a pencil, follow along, actually work through the examples alongside me. And that way you can also make notes of things like, ooh, I'm not so sure about that. Maybe I should meet with Mr. Maxwell later and ask him some questions about that part. And you can kind of keep track and know where you're stuck and take notes of the things that you need to. Okay, so I recommend go get a pencil. If you want to print out these notes, you absolutely can, but it's not mandatory. You can also just work on loose leaf or whatever as well. Okay, but there is space for you to work in the notes. So if you print them out, you can just work directly in them as well. Okay, so without further ado, I guess we'll get going here on Unit A, Lesson 1, Chapter 9, Momentum. Here we go, Physics 30, exciting. So the first unit of Physics 30 is just one chapter, just Chapter 9, and to be honest, this unit kind of fits better in Physics 20, to be honest. There's just not much room in Physics 20, we already do so much, that they throw it into Physics 30 instead. And the reason I say that is that it has a lot to do with analyzing, calculating, and looking at the motion of objects, which is what Physics 20 was all about. I'm sure you remember, at least a very good chunk of it was all about the motion of objects and how we can analyze and measure it in different ways. Okay, and so we're going to introduce another way of analyzing and looking at the motion of objects in Unit A here of Physics 30, and that is momentum. Okay, a term you've probably heard used in everyday life all the time, but it is a physical quantity and it does have a well-defined physical meaning. So let's talk about that. So like I said, we're going to use momentum to analyze interactions between objects. Not always just interactions, meaning two or more objects interacting with each other, but even just the motion of one object can be analyzed with momentum. That's mostly what we'll look at today. Okay, but things like collisions and explosions, momentum is incredibly useful for. We will use it in those contexts. Okay. We can also, and we'll do this today, use momentum to study the forces and the times involved in a collision, and therefore how damaging a collision can be, that type of thing. You hear this term thrown around. This is what Isaac Newton said when he talked about momentum. He defined it as the quantity of motion. What does that mean? It basically means like how much oomph does this thing have, right? I know oomph is not a proper scientific term, but one way to look at it, a good question to ask, right, to say like, does this object have a lot of momentum, is how hard would it be to stop this object? Okay, so an example of something with a lot of momentum would be like a very big truck going very fast, right? That's kind of a hard object to stop. Okay, looking at the equation here, we can kind of see what two things make up momentum. So momentum has the symbol P, just because M was already taken by mass, basically, right? It has a P, and notice there's an arrow above it, meaning that it is a vector. We'll talk about that more in a second, okay? And it's actually just mass times velocity. This is the formula for momentum. It's actually a very simple equation, right? Take an object's mass, multiply it by its velocity. Looking over at our formula sheet here, you can see momentum and energy. There is where you will find the formula for momentum, okay? And so you can kind of see, right, a little bit, how do you get a lot of momentum? You can either have a really big mass or a really big velocity, or both, right? Be moving really, really fast. That would give you a lot of momentum. Be really, really large. That would give you a lot of momentum. If you've got both, right, very big mass and moving very fast, then you really have a lot of momentum. So can you kind of see now how hard would it be to stop this object? Now that we see the two ingredients to momentum, mass and velocity, does that kind of make sense, right? If something's going very, very, very fast, it's harder to stop. Also, if something's very, very, very large, it's harder to stop, right? And large and moving. Another way I often think about this, yes, how hard would it be to stop this object? But another good way to think about it is, you know, how much would you not want to be hit by this thing? If the answer is, I really don't want to be hit by that, then it probably has a lot of momentum, right? So if an object, right, I mean, picture this, a truck that's moving incredibly slow, you still kind of don't want to get hit by it, right? it still has a pretty big mass, and therefore it still has a pretty big momentum. Okay, but if its velocity is very, very, very high, right, then you definitely don't want to get hit by that truck. It has a huge momentum, right? And I mean, take this down to the scale of things like, you know, a little ball. If I took a ball and threw it at you, it doesn't have that much mass, so it's not very nice of me, but it's not going to really hurt if I throw a ball at you kind of softly, right? Why? The velocity is very low, and therefore it doesn't have that much momentum, right? But now if I take that ball and I put it into a cannon and I fire it at you very quickly, well now, yeah, you really don't want to get hit by that, right? So this is kind of another way of thinking about the amount of oomph, the quantity of motion, right? That's what momentum is. How hard would it be to stop this object? How bad would it be to get hit by this object? That's kind of one way you can give yourself an intuitive feeling for what momentum really is. Okay, let's try out our first example here. So it asks us, what are the base SI, that's Standard International or System International, units of momentum? So remember, our base units, those are things like kilograms, meters, and seconds, right? We can make what we call derived units. For example, the Newton is a derived unit. It is standard, but it's really, when we break it down, it's a kilogram meter per second squared. That just comes from force equals mass times acceleration. Mass base units is kilogram, acceleration base units is meters per second squared. So a force in newtons, really though, a newton in base units is a kilogram meter per second squared. So it asks us, what are the base SI units of momentum? And just a reminder here, right? We do need to be able to figure this kind of stuff out on our own for any quantity, but it's not something to memorize. It's based on the formula. The formula tells us what the base units of momentum should be because it's mass times velocity. So what do we measure mass in? Well, we measure mass in kilograms. So we use square brackets when we're just talking units. We're not actually doing math here. We're just saying, what would the units be? Mass is measured in kilograms. Velocity, you know, is measured in meters per second. So momentum is measured in kilogram meters per second. Kilograms times meters per second. That is the base unit of momentum. We don't give this one its own name. Not sure why we didn't decide to derive a unit for it, but honestly, it's better this way anyway. We have the base units. This tells us the equation for it is mass times velocity, and it kind of gives us all the information we need. So that's how we measure momentum, kilograms meters per second. Then it asks, is momentum a vector or a scalar? Now, I kind of already gave it away earlier. I said it, but let's pretend I didn't. Look at the formula. Is there a clue here that momentum is in fact a vector? Yeah, look. The little arrow above the P, right? I mean, that's how we know that this is velocity and not speed. If it were speed, it would just have the symbol V, right? It would be a scalar. But putting the arrow above it tells us that it's velocity, it's a vector, it has direction. Direction matters, okay? So it is a vector. And it asks, how did we know just based on the formula? Well, the arrow, right? The arrow, and that's on our formula sheet as well. So if we ever forget that momentum is a vector, right, it's right there to remind us. Momentum is a vector. Direction matters, okay? Which leads us into the next part of this question here. What does it mean for it to be a vector? Well, it means that direction matters. It makes a difference. Doing the same thing in the opposite direction is not actually the same thing for a vector, right? A reminder from Physics 20, the simplest example of a vector versus a scalar is your displacement versus your distance, right? I always use the example of if you drive 300 kilometers south to Calgary and then 300 kilometers north back to Edmonton, the total distance you've traveled is 600 kilometers because we're not worried about direction there, right? But the displacement you've moved through is actually 0 kilometers because the 300 kilometers to the south and the 300 kilometers to the north together are in opposite directions and they cancel each other out, right? So a momentum of 100 kilogram meters per second to the east is not the same thing as 100 kilogram meters per second to the west. They have the same magnitude, the same size, but they do not have the same direction. And since it's a vector, that means they are not the same, right? They're not. Direction is important to a vector. So whenever calculating anything to do with momentum, we do need to be thinking about direction, right? And therefore often the correct sign, as that's the signs are how we keep track of things in opposite directions, positive or negative, I mean by signs, okay? So we must consider direction when working with momentum. It's a vector. Direction is important. One of those kind of things I say, like a test to see if something's a vector, is ask yourself, if you do the same thing but in the opposite direction, do you just make it bigger or do you cancel it out, right? Force is a vector. If two people push on an object with the same force but in opposite directions, they just cancel each other's forces out and the object doesn't go anywhere, right? Energy is a scalar. The same thing in opposite directions doesn't cancel out. You can't run downstairs, burn up some energy, and then run back upstairs and cancel that energy out, right? You just actually use more energy by doing that. Okay, let's try out our first calculation example here. So what is the momentum of a 10,000 kilogram rocket? Again, reminder, as we work through, we see important information. Let's just make note of it right away. M, our mass, is 10,000 kilograms. For a 10,000 kilogram rocket that's moving upward at 4.6 kilometers per second. So that is a velocity, but note something here. We always want to work in standard units, right? Are kilometers per second the standard unit for velocity? No, right? We want meters per second. So let's just list out our givens here so that we have them ready to go. And our velocity is 4.6 kilometers per second. But there are 1,000 meters in every kilometer, right? Those conversion factors are on the back of your formula sheet if you're rusty on them, but kilo means 1,000. So we want to convert these kilometers per second into meters per second. To do that, we're going to need to cancel out the kilometers, right? Replace them with meters. And 1,000 meters is the same thing as 1 kilometer. And this is okay now because really what I'm doing is I'm multiplying this by 1, right? Because 1,000 meters is 1 kilometer. So I'm not going to change what this is. I'm just going to change how it's being measured. It still means the same thing. We can double check our work, make sure the kilometers cancel out, and they do because we have kilometers on top being divided by kilometers on bottom, right? Leaving us with meters over seconds, meters per second. So sure enough, 4.6 kilometers per second is 4,600 meters per second. And that makes sense, right? If a kilometer is 1,000 meters and we've gone 4.6 kilometers every second, it makes sense that we've gone 4,600 meters per second, right? That's just 4.6 thousand. Okay. Now, very important, I'm missing something there. This is upwards. It is a velocity, so I do need to give it a direction. Okay, and when it comes time to do the math, how do I work with direction? How do I make sure I'm keeping track of directions and that opposite directions are working against each other for vectors? Well, we can assign signs, right? So the most common would be to call up positive, and then the opposite of that, which is down, negative. So when I go to actually do math with this, I don't have an up button on my calculator, but what I can do is say that I'm defining up as positive, and I'll make this a positive number. And then if I get a positive answer, I know that it means my answer was upward, right? Assuming my answer is a vector, but it is in this case because what we're looking for is the momentum of the rocket. So there's only one equation for this job, right? We have the mass, we have the velocity, and we want to find the object's momentum. So momentum equals mass times velocity, right? It's right there on our formula sheet. Okay, so the momentum of an object is equal to its mass times its velocity. So I can take the mass of the rocket, 10,000 kilograms, and multiply it by its velocity, which we now know is 4,600 meters per second upwards. So I'll make it positive there. And multiply those two together, we get that the momentum of the rocket is 4,600,000. What would my units be? Kilograms, meters per second, right? We're multiplying kilograms by meters per second. So those are our units, the units of momentum, so that's a good sign. Okay, now, we only have 2 significant digits in the least number we were given, right? This has 5, but this has 2. So remember, that limits the precision to which we can record our answer, right? We don't actually have that much confidence that it's 4,600,000, right? It could be like a 1 here or a 2 here, because this is only given to 2 digits of precision. We can't claim to know this to that many digits of precision. So we're going to need scientific notation here. Remember, right, there's a decimal here. Scientific notation is always a number between 1 but less than 10. So like from 1 point something to 9.9 something, right? Times 10 to the power of however many times we need to multiply it by 10 to get our actual number. So what I mean by that is this would be, right, 4.6 to 2 significant digits, because that's what we get, times 10 to the power of 1, 2, 3, 4, 5, 6, 7. So 4.6 times 10 to the 7th power kilogram meters per second. Okay, and all that's saying, again, this is equivalent to 4.6 times 10 7 times, right? Which it is. Like, this is 4.6 if you multiplied it by 10 7 times. This is just a more convenient way to represent larger numbers, and it also lets us represent it to the 2 significant digits we were allowed. Now, I'm missing something very important in my final answer, because this is momentum. Momentum is a vector. So this is an incomplete answer because I have not stated what direction, right? This is not a full description of its momentum. This is its magnitude, its size, but until I add that, it was not actually the full answer for momentum. Momentum has magnitude and direction. Okay, so the momentum is in the same direction as the velocity. That's not surprising, but the math backs us up there. We define velocity upwards as positive. We got a positive momentum, so the momentum being positive tells us it was also upward in the same positive direction. All right, let's try this one. So after expending some fuel, the rocket from the previous example has had its mass decreased to 3/4 its original value, and its speed has increased by a factor of 2. What is the rocket's momentum now? So it's saying that, it lost some fuel, so it got lighter, but it also got faster, and we want to know what would be its new momentum, okay? Well, the equation can let us figure that out because we know momentum is just equal to, I'm going to leave some room here to write in some changes that have happened. It's equal to mass times velocity, right? But the mass has been changed. And we can see from the equation, like doubling the mass would double our momentum because this becomes twice as big. So that's going to become twice as big, right? Our answer would become twice as big. Doubling the velocity would also double the momentum, right? Doubling this gives us an answer 2 times bigger now. So what's happened is that the mass has been decreased to 3/4 its original value. So the mass has essentially been multiplied by 3/4, right? And the velocity has now been multiplied by 2. It's increased by a factor of 2. It got 2 times faster, okay? So I'm just going to put a little apostrophe symbol here. It's prime. It just means the new momentum, essentially, right? What is our new momentum if these changes have happened? Well, multiplying the mass by 3/4, just that would decrease the momentum by a factor of 3/4. But that's not the only thing that happened, right? The mass lowered, and that on its own would decrease our momentum. But at the same time, the velocity actually increased. So we want to figure out what's the overall effect then to the momentum. Well, we've got 3/4 m times 2v. This is just, 3/4 times 2 times the original mass times the original velocity, right? Our original mass got multiplied by 3/4. This is representing now our new mass. Our original velocity got multiplied by 2. This is our new velocity. So this can tell us what our new momentum would be, right? This is our original mass times our original velocity. That's actually our original momentum then, isn't it? Momentum is just mass times velocity. So this is showing us by what factor our original momentum has been multiplied. So we can see here, 3/4 times 2, remember you can think of 2 as 2/1, right? So this is 6/4 times mv. That's our original momentum, okay? 6/4 can be reduced as a fraction to 3/2, okay, times mv. So our new momentum is just 3/2 times our original momentum, right? This is just the original momentum. We changed the mass by multiplying it by 3/4, it says, and we changed the velocity by multiplying it by 2. So take our original mass times 3/4, original velocity times 2. That should give us the new momentum, okay? So we know the original momentum. It was 4.6 times 10 to the 7, or 46 million kilogram meters per second, right? So what's the new momentum? Well, take the original and multiply it by 3 over 2, right? So new momentum is 46 million kilogram meters per second times 3 over 2, or 1.5. And so multiplying that by 3 over 2, you get 69 million kilogram meters per second, which to two significant digits using our scientific notation would be 6.9 times 10 to the power of 1, 2, 3, 4, 5, 6, 7 kilogram meters per second, and still upwards. All right, let's try this one out. So it says a 1,200 kilogram car, okay, we know it's mass then, let's just make note of that, has a kinetic energy of 3.3 times 10 to the 5 joules. So that's EK, the kinetic energy. What is the magnitude of its momentum? So notice here, they didn't give us enough information to figure out the direction. We can figure out the magnitude, the number, but we can't actually say the direction here. And that's because energy is a scalar. And so this isn't going to give us direction, right? Energy is a scalar. And they haven't told us the direction either. So best we can do here is get the size of the momentum, but we won't know its direction. Okay, so we know there's only two things we need to find an object's momentum. It's mass and its velocity, right? We have the mass, so check, but we don't have the velocity, right? Or even the speed. But we were given the kinetic energy, right? So if we remind ourselves, and again, it's on our formula sheet, you don't have to memorize anything for physics, that's the nice part about it, okay? The kinetic energy, you might remember, it's in the energy section unsurprisingly, it's 1/2 mass times speed squared, or a lot of students, and honestly I fall into this category as well, I prefer to write it this way, I just find it easier to work with, right? Means the same thing, 1/2 is the same as dividing by 2, so mv squared over 2. Okay, well, could we use that then, right? Could we find the speed using the kinetic energy equation? Because we have the mass, right? If kinetic energy is equal to mass times speed squared over 2, and we have the mass, and we have the kinetic energy, well, hey, the only thing we don't know in that equation is the speed, which means we can solve for it. So we can solve this for speed. Let's do a little reminder of how to manipulate equations, okay? Because right now we don't have this isolated for V, which is what we'll need. So if kinetic energy equals mass times speed squared over 2, we want to isolate speed. The problem is it's not by itself because operations are currently being performed on it, right? So what we do is we undo those operations with the opposite operation until it is by itself. Now, since we're undoing those operations, we have to follow not BEDMAS, but SAM-DEB, the reverse order of operations. And that's just because, again, we're not doing the operations, we're trying to undo what's happening to V. It's like getting unpacked after a vacation, right? You're reversing the order you packed in. So the order you put the stuff into your suitcase is the opposite order of how you're going to take it out when you get home, right? The stuff on top has to come out first, even though it's what went in last. Kind of the same idea here. We work outer to inner. So one at a time, I need to do the opposite of operation of what's happening to speed until it's by itself, following the reverse order of operations. So I see that speed is being squared. That's an exponent. And it's being multiplied by mass and divided by 2. So multiplication and division, I can deal with them at the same time, even if I want. But for the way it's set up here, I think the easiest first thing to do, we're dividing by 2. So to undo that, let's do the opposite operation of dividing, which is multiplying. Multiply both sides by 2, and things will look a little bit better. And so after multiplying both sides by 2, we now have that 2 times the kinetic energy is equal to the mass times the speed squared, and we just repeat that process. V is being squared, but that's an exponent. First, I have to make sure I've dealt with all multiplications and divisions. So it's also being multiplied by mass. So to undo that, we'll do the opposite of multiplying by mass. We'll divide by mass. And there we go. And so we're almost there. V is being squared now. That's the only thing happening to it. So to undo something being squared, we take the square root. What I do to one side, I must do to the other. Otherwise, they're not equal anymore. And we get that the speed is the square root of 2 times the kinetic energy over the mass. Now we're ready to plug in and solve for the speed. So the speed will be the square root of 2 times the kinetic energy. Our kinetic energy is 3.3 times 10 to the 5 joules over our mass. Our mass, we were told, is 1,200 kilograms. And so putting that into my calculator, right, 2 times 3.3, you can use the E button. That's the capital E on most calculators to do times 10 to the power of 5. So I would do 2 times 3.3 E5, divide by 1,200, and then square root all of that. When I did that, I got 23.4521 meters per second. Okay, always keeping our unrounded answer at least 4 or 5 digits after the decimal, okay, because if we keep rounding, if we over round, then by the end, our answer can actually be off by a little bit, right, by a 10th or a 100th or something. And on a numerical response question, like on the diploma, it's either right or it's wrong. So like if we over rounded and it ended up changing our final answer by a little bit by the time we got done, we would just get marked wrong. Okay, so always be careful. Remember to keep extra digits until it's the very end and it's time to round to the correct number of sig digs. Okay, but we're not done because we didn't want to find the V. We wanted to find P, right? We wanted to find momentum. Okay, now this is speed. This is not velocity, right? Because this is kinetic energy. It's a scalar. It doesn't depend on velocity. It actually only depends on speed, how fast the object is moving, not how fast and in which direction. And so that's why we can only really find the magnitude of its momentum, right? Speed is sort of, I mean, there's a little more to it than this, but speed is like the magnitude of velocity. It is how fast you're going, but it's not how fast you're going and in which direction. So we can find how much momentum it has because we do know how fast it's going, but we can't find the direction of that momentum. And that's why all we'll be able to do here is find the magnitude of the momentum. So if we really want, we could say this, right, indicates magnitude. It's like absolute value in math class. It's just saying what we're about to find is not the full momentum because we're not going to be able to get direction, but we can at least get how big it is. And we know that momentum is mass times velocity, okay? We have the speed, so we can get that it is 1,200 kilograms, and the speed is 23.4521 meters per second, showing us that the magnitude of the momentum is going to be, I got 28,142 kilogram meters per second, or to 2 significant digits, because we did use this number, so that limits the accuracy of our answer and the precision we can state it to, right? 2.8 times 10 to the 4 kilogram meters per second. That's the magnitude of the momentum. We don't have the direction, but we didn't need it for this question. All right. Okay, so 2 steps there, right? First, we found V, and then second, we used that speed to find the magnitude of the momentum. So inserted in the notes here are little like checkpoint, try it out yourself type questions. Okay, so I always encourage you when these come up, pause the video and actually do take some time to practice it, right? Physics is like riding a bike. You can't learn it just by watching someone else do it, right? You can't watch someone ride a bike and learn how to ride a bike. You eventually have to get on the bike and do it yourself. That's where the real learning happens, okay? So go ahead, pause the video, try at least this one. These come straight from your practice problems that are assigned to you, so you can get a few of them done just while you watch the video lessons. Okay, and there are more questions on that page or nearby that you from your assignment that you could try out as well. Okay, so at a minimum, try this one, but you can look there too and see a couple others. If you say, you know what, I could probably do that too. Now that I know how to calculate momentum, feel free to try a few. Take a little break from my voice. I know these videos can get kind of long when we're cramming a whole course into a quarter, but at the very least, try this one. See how it goes. If you have any troubles, don't forget to reach out to me, book a meeting, okay? And then we'll continue on with some more examples. But take a little break, try it out while it's fresh in your brain. All right, so moving on here now to talk a little bit about graphical analysis and remind ourselves of the important skills from Physics 20. Okay, it asks us to sketch a momentum as a function of velocity graph. So reminder, as a function of, it's always y as a function of x. When that title is given, right, that means we're going to graph momentum on the y-axis, velocity on the x-axis, right? It's dependent variable as a function of independent variable, or responding as a function of manipulated, you might sometimes say. Okay, and again, that kind of checks out, right? The momentum depends on the velocity. That makes a little more sense than saying the velocity depends on the momentum. So that as a function of, that takes all guess out of it. Momentum is going to go on our y-axis. Velocity is going to go on our x-axis. Then it says, derive the equation you would use to determine the mass of the object with this graph. Okay, maybe we're getting a bit ahead of ourselves though. We haven't even finished sketching our graph. So the question is, how does this depend on velocity? What's going to happen to the y value as the x value increases, right? Well, the equation tells us. The equation is just the relationship. It shows us how momentum is related to velocity, right? So we can ask ourselves here, first things first, when velocity increases, what's going to happen to momentum? Let the equation tell you. You don't have to guess, right? If this goes up, what happens to my answer? Do I get a bigger answer or a smaller answer? I get a bigger answer, right? So there's one thing. As x increases, as velocity goes up, y will also increase. Now the next question is, what kind of shape does it follow? Is it linear? Is it going to be a straight line, right? Or is it going to be curved? So when we double the velocity, what do we do to the momentum? I think we just double it, right? There's no squaring or square rooting or anything funky like that going on. If I triple the velocity, I triple the momentum. If I quadruple the velocity, I quadruple the momentum, right? It's a direct linear relationship. We represent that like this. It's not saying that P equals V, but it's saying this is how momentum depends on just the velocity. Yes, mass matters too, but if we just want to look at the relationship between those two variables, this is saying momentum is directly and linearly proportional to the velocity. Not, velocity squared or square root of velocity or something that would give us a curved graph. It's just straight up linearly directly proportional to the velocity. Meaning we'll get, what do we say? We said a line as x increases, so does y, okay? And it always increases by the same factor. So that gives us a straight line, right? For every constant change in velocity, the proportional change in momentum should be the same. Cutting v in half should cut momentum in half. Doubling v should double momentum, and on and on. Now moving on to this here, it asks us again to derive the equation we could use to determine the mass of the object with this graph using graphical analysis. So stop. Remember, graphical analysis, we are always interested in one of three things. It's either the slope, the area under the graph, or one of the intercept, right? It's always slope, area, or intercepts. I find sometimes students overcomplicate graphical analysis in their mind and they're like, what am I supposed to do with the graph? It's one of those three things. Okay? And it's not a guessing game. It is not something to be memorized. I find students who struggle with graphical analysis are the ones who try to come up with like a rule they can memorize or something like that, right? The equation tells us whether we want slope, area, or whether we're interested in one of the intercepts. Because look, momentum equals mass times velocity, right? We're asked to derive an equation that could be used for graphical analysis to determine the mass. Well, divide both sides by velocity to solve for mass, and then look at what the equation tells us to do with y and x. It says take the momentum, well, that's on our y-axis, and divide it by the velocity. That's on our x-axis. So we're dividing a change in y over a change in x, right? This is y over x. It is a change in y. Do you remember the name we have for that? That is a rise over a change in x. That's a run, right? We're just doing rise over run. How much did the graph go up over how much it went sideways? In other words, we could find the slope of this graph, and that would be telling us the mass of this object. For every x change in velocity, we get y change in momentum, and the rate at which that momentum changes with respect to the velocity just has to do with how big the mass was, right? Another way to look at it, we can always use that y equals mx plus b form of a line, right? So if we compare that to the equation momentum equals mass times velocity, well, we know velocity is on our x-axis. We know momentum is on our y-axis, right? So look, it's already in y equals mx plus b form because y is isolated. So y equals mass times velocity is y equals mx. So our slope is the mass. Same result, looking at it a slightly different approach. Okay, so there we go. Notice I didn't just pull slope out of thin air, right? I let the equation tell me. You could have no idea what these variables mean, but if I gave you this equation and asked you what, and I gave you this graph, right? And I said, how would you find mass? Even if you had no idea what m meant, right? The equation would still have told us, oh, we're going to divide the y by the x. That's a rise over a run. That's the slope. Okay, just a reminder of some of the terminology. We'll be seeing all kinds of these graphs as we go through Physics 30, as I'm sure you could predict, okay? So I'll just give you some reminders of the terminology. We've already seen this one, linear, direct. Direct just means as one gets larger, so does the other, right? So if you make one thing larger and the other variable also gets larger, we say those have a direct relationship. I mean, an example would be velocity and momentum. Bigger velocity results in bigger momentum. And linear just means it changes by the same factor. So doubling the velocity, for example, also doubles the momentum, right? There's no squaring or anything happening like that. So there we go. That's a linear direct relationship. Notice for the same change in x, the same run, there's always the same change in y, the same rise. No matter where I draw that little triangle, you know, if I try to do it again here, if I draw the same run, I will get the same size rise. They're always changing at a constant rate relative to each other, giving us a constant slope and therefore giving us a straight line. Now, having completed Physics 20, we know that some relationships between variables are not linear, right? Some are curved, meaning that, like, for example, just to pull one up, right, that we've seen before, kinetic energy and speed. Kinetic energy is not linearly proportional to the speed. It's proportional to the speed squared, okay? Meaning that if I double the speed, I don't actually double the kinetic energy. And that's because in the equation, speed gets squared, right? So for example, if I take v and I replace it with 2v, I double the speed, in other words, well, that factor of 2 gets squared, right? Just, you know, if the speed was 1 meter per second and it's now become 2 meters per second, v squared has gone from being 1 to 4. It got 4 times larger, and it's because of that squaring that's going on, right? So there are relationships that are direct, meaning when one gets bigger, the other one gets bigger too, but it doesn't actually always get bigger by the same factor. So it might look like this. That would be what kinetic energy and speed, right? This is what a EK as a function of speed graph would look like. Because again, at first, you know, changing 1, square that, you get a change of 1. But then later, change by another 1 to get to 2, suddenly you're going up by 4. And then another 1 to get to 3, suddenly you're going up by 9, right? 3 squared is 9. So notice it's not always the same change relative to each other. The rise is getting steeper and steeper, while the run stays the same size, right? Or we could also actually have, this would be a curved direct relationship, something like this. Still, as speed gets bigger, this isn't what speed and kinetic energy would do, but still, as x variable gets larger, y variable is getting larger. So it's still a direct relationship, but it's getting larger at a slower and slower rate, right? The rise over run, the slope is not constant. The rise is getting smaller and smaller, even if I keep the run the same, right? So it is direct. As x gets bigger, so does y, but it's curved. It's not linear. All right, and the last type is an inverse. And so inverse means that as one variable increases, the other actually decreases. So as x goes up, y goes down, and vice versa, right? As x decreases, y increases. An example of this you've seen before is, you've seen a few, but one is the force of gravity and the separation distance between the two objects, what we call r, right? We can see that as the distance between two objects gets larger, the force of gravity between them should get smaller because we're dividing by r, right? In fact, we're dividing by r squared, so it's actually an inverse square relationship, right? So the bigger the r is, the smaller our answer is for FG, okay? So that gives us an inverse relationship, and those actually look like this. They're not actually straight lines like that, which throws students off at first. Sometimes they say, I see why an inverse square might have the shape, but what about like just, v equals d over t or something where the t isn't being squared? Would t and v also have a graph like that? It actually would, okay? And the reason is that if we take a look, right? I made a little table of values here to think about an inverse relationship. So notice the slope is very, very steep when x is small, and then the slope gets very, very small when x is large. So we're getting a really big change in y for a very slight change in x, right, over here, and then reverse that. We're getting a very small change in y, even for a large change in x on this part of the graph. So to emphasize why that is, I just made a quick table of values for an inverse relationship. Let's say we have some variable x and some variable y that's related to x inversely. Y is equal to 1 over x, let's say, right? So when x is 0.001, y will be 1 over that, which is 1,000, right? So if we increase x by, relatively speaking, a pretty small amount, right? We change it by 0.009 to get 0.01. Y actually changes by a much bigger factor. 1 over 0.01 is 100. So that's a change in y of negative 900, right? It went from 1,000 to 100, while x just went up by 0.009, right? X went from 0.001 to 0.01. Y got smaller by a factor of 1/10, right? It went from 1,000 to 100. So very big change in y for a very small change of x. You can see that's the case when x is small, right? Very small changes in x are happening here, but very large changes in y result because of that inverse nature. Well, look at that, right? When x was very small, small increases in x lead to large decreases in y, relatively speaking, right? Even this tiny little change in x causes a pretty significant change in y on our graph. So that matches up, right? And then reverse that. When x is very large, well, y is inversely related to it. So when x goes from being 10 to 100, for example, y is going from being 1/10 to 1/100th. So pretty big change in x, changed by 90, right? But y only changed from 0.1 to 0.01, a change of 0.09, right? Big change in x here, right? 100 to 1,000, a change in 900 of x, right? Only caused a change of 0.009 of y. And that's exactly what we see. As x gets larger and larger, it causes smaller and smaller changes in y, right? A less dramatic slope. Even a very big change in x doesn't lead to that impressive of a change in y. Okay, so just to give you some intuition for why inverse graphs are shaped like this and not like this. We see they're not linear. A table of values can help us see why. Okay, so there's a reminder of the graph terminology. It won't come up much in this unit, but we will do it in later units, okay? But I want to mention it now while we're reminding ourselves of some graph stuff. We'll gain more experience with the skill of something called graph straightening, in which we choose our plotted x and y quantities carefully so that when we graph them, they produce a straight line, okay? Now, why would we want to do this, it asks. Why is a straight line essential for any kind of graphical analysis? Pop quiz, do you remember? There's 3 things always that we might care about when doing graphical analysis. It's always one of those 3 things. Do you remember what they were? It is always about slope, area, or intercept. right? And so we need a straight line because what is the slope of that? Well, that's not a great question because it has many different slopes, right? The slope there is very different than the slope here, for example, right? It's running and rising a very different amount there than it is there, okay? And so we can't find the slope of that, right? Area, I mean, it does have an area, but how are you supposed to find it? We don't have a formula for the area of a shape like that, right? So without learning calculus, we need a straight line to be able to find slope, area, or intercept. All right, so moving on here, let's return back to talking more about momentum, okay? Specifically, we're going to talk about how they connect to Newton's laws. In fact, when Newton wrote these three laws, which is not hyperbole or exaggeration to say that these are three of the most important ideas in physics, okay? We use them so much, it's not even funny. And actually, when Newton wrote them down, he was actually kind of thinking about them in terms of momentum and changes in momentum. Okay, so Newton's first law is what we often call the law of inertia. All it says is that an object at rest or in uniform motion will remain in that state unless acted upon by an unbalanced net force. Now, what does that mean? It just means objects will keep doing what they're doing unless some net force causes them to change that, right? So, your calculator sitting on your desk right now, the forces acting on it are all balanced. There's no net force overall acting on it, and so it's going to continue to sit there, right? To make it accelerate, to make it change its motion, you would need to push it or pull it or move it so that gravity can be unbalanced and pull it to the floor. Essentially, all it's saying, right, this is Newton's first law, it's that if the net force acting on it is zero, then its acceleration is zero. Notice I didn't say its velocity would be zero, right? An object can be moving as long as it's moving with uniform motion. That object could still be experiencing Newton's first law, right? It won't change how it's moving. So it could be going 100 kilometers per hour in a straight line. But if it's not speeding up, slowing down, or changing directions, right, then the net forces acting on it must be zero, and it's going to continue to do that. An object at rest or in uniform motion. So this is physics principle number 0. Okay, all I mean by that, we're going to reference those more and more as the diploma gets closer and closer, okay? Because the diploma likes to ask you, which physics principle did you use to answer this question, or something like that, right? And they're just asking you basically to think about what knowledge are you applying, right? So this is just an Alberta thing. If you asked a BC student, what's physics principle number 0, they wouldn't know what to say. But we just give them numbers so that you can fill out a numerical response question, right? If it asks you, what actual physics knowledge were you applying to answer this, right? If it's something where we had to, calculate, we said, okay, the net force on the object was 0, so its motion won't change, then we would say on a numerical response, we were applying physics principle 0, right? This is just the back of your formula sheet. They give you all those physics principles there. Okay, Newton's second law. It's very closely related to the first law, okay? And it just says that an object will change its motion when acted upon by an unbalanced force, right? So the first law says if there's no net force, it won't accelerate. The second law just says if there is a net force, it will accelerate. And it says a bit more than that, okay? It says that the acceleration will be directly proportional, meaning that when one gets bigger, the acceleration also gets bigger, okay? Will be directly proportional to the force. So that makes sense, right? Bigger force, bigger acceleration. If you want to change an object's motion more, you push it harder. It will also be inversely proportional to the object's mass. So a bigger mass results in a smaller acceleration if the same force is used. Again, that checks out, right? If you push a bicycle versus pushing a pickup truck, you're going to be able to change the bicycle's motion more because it has less mass, okay? And the acceleration will also be in the same direction as the net force. So Newton's second law is honestly best summarized by an equation. one that you know and love from Physics 20, and that is that the acceleration is equal to the net force, the total force acting on the object, divided by its mass, right? This tells us all of this information. If the net force isn't zero, then the acceleration won't be zero. So that tells us the object will accelerate if there's a net force, right? It also shows us that if the net force is larger, bigger numerator, we get a bigger acceleration as a result. And it also tells us that if the mass is larger, we're dividing by a bigger number, so we get a smaller acceleration as a result. So in terms of physics principles, you can see on the back of your formula sheet that this is physics principle number 1. We apply it for accelerated motion, or we can anyway apply it for accelerated motion, right? When F net is not 0 and the object's motion is therefore changing. This is going to come into play as it relates to momentum. This is having to do, if you change your velocity, right? You change your motion, you're changing your velocity. Acceleration is the rate at which your velocity changes. So if you accelerate, your velocity's changing, and now we know that that means your momentum is changing, right? So Newton's second law is going to have some implications for changes in momentum, which we will come to call impulse. We'll introduce that term in this lesson as well. Okay, so just connecting it to momentum here. That's why we're bringing these up. And last but not least, Newton's third law, which just states that when two objects interact could mean and often does mean like touch, like run into each other or push off of each other, but it doesn't always have to be touching, right? We know from Physics 20 that the force of gravity follows Newton's third law, right? Earth pulls on the moon pulls back on the earth, or even you pull up on the earth as it pulls down on you through its force of gravity, okay? But when two objects interact, they exert equal in magnitude, so the forces are the same size, but opposite in direction. Forces on each other, right? So I mean, which direction do you push the earth in order to jump? You push it down, and then through Newton's third law, the earth pushes back up on you, allowing you to accelerate upwards and jump, right? So as an equation, we would say that the force of object 1 on object 2 is equal but opposite to the force of object 2 on object 1, okay? So this does not get its own physics principle number. However, this does lead to something very important. It leads to our first new physics principle for Physics 30 that we did not see in Physics 20, which is physics principle number 4. Something we'll be looking at in the next 2 lessons, the law of conservation of momentum. We'll see how in the next lesson that this Newton's third law actually gives us one of the fundamental laws of the universe, the law of conservation of momentum. Okay, but we'll put that on the back burner for now. Let's actually, what we're focused on here is actually this part, the connection of Newton's second law to how changes in momentum occur. And it comes from thinking about the relationships embedded in what we already know about Newton's second law. And also how those relate to the new relationships we now know about momentum. Okay, so Newton's second law, acceleration will be directly proportional to the net force acting on the object divided by the object's mass. Okay, rearranging this, multiply both sides by mass, we get the net force is equal to the mass times the acceleration. Okay, now we're trying to see its relationship to momentum. We don't have velocity in this equation. We do have mass, but like we know momentum is mass times velocity. So could we make a substitution here to make velocity show up? Well, acceleration, remember, if we check your formula sheet, acceleration is just the rate at which velocity changes. In other words, it's the change in velocity divided by how much time went by, right? How much did its velocity change divided by how long it took to make that change. So if acceleration is just velocity, change in velocity over change in time, then we could write this as F net equals mass times, yes, acceleration, but acceleration is a change in velocity over a change in time. Now, I see that we've made, mass times, not quite mass times velocity, but mass times a change in velocity has now showed up in our equation. So we're getting closer to thinking about the relationship to momentum here. Let's just make that right side look more like m times v. Let's multiply both sides by time, and that will just give us that the force, I'm just going to drop the net, the force times the time that's gone by will be equal to the mass times the change in velocity. Okay, we're getting there. This is sort of like momentum, but be careful. It's not quite momentum, right? Momentum is, it's not about the mass times the object's change in velocity. To find something's momentum, we just take its mass and we multiply it by its velocity. So let's expand this out a bit. Now, how do you find a change in anything? Do you remember? What's the difference in your age? What's your change in age since you were 10 years old, right? Well, you would take your age now, final, and subtract your age when you were 10 years old, the initial age, right? And that gives you the change in your age, right? Subtract them, that gives you the change in age. Final minus initial is how we find how much something changed by. So change in velocity is just saying the final velocity, what it ended up with, minus the velocity it started with, final minus initial. This is how much its velocity changed by, right? And okay, we're getting close now to seeing how momentum is involved here, because look, mass times velocity final, just distributing this mass into those brackets, minus mass times velocity initial is equal to the force times the time that that force was actually acting. Now, what is mass times final velocity? Well, mass times velocity is just the momentum, right? So mass times final velocity is just the object's final momentum, the momentum that it ended up with. And similarly, mass times initial velocity is just its initial velocity. Sorry, initial momentum, right? This is just final momentum. This is just initial momentum. So the force that was acting on the object times the time that it was acting for will tell us how much the object's momentum should change by, right? Final minus initial just gives us the change. This is actually how Newton wrote his second law. If you were to travel back in time and ask Isaac Newton what his second law of motion was, he actually would have said this. He wouldn't have said A equals F net over M. Now, we've seen they're mathematically and they're talking about the same thing, right? But this is actually how Newton was thinking about it. He said that a force acting on an object for a given amount of time will cause that object's momentum to change. Okay. Now, this change in momentum actually has a special name, or change in momentum in general has a special name. We call it, and I referenced this term earlier, we're about to get into it for real now, this change in momentum. A change in momentum is what we refer to as an impulse. The impulse experienced by an object is just saying how much it did its momentum change by. So if we take a look on our formula sheet here, you will see this. This is how Isaac Newton would have said his second law was supposed to be written, right? The force acting on an object for a given amount of time will cause its momentum to change. Okay, so here is a formula that comes in very handy. Force times the time is equal to the object's mass times its change in velocity. But notice, it's just Newton's second law, as we know and love it, right? Rearranged and played around with a bit, right? If I divide both sides by t, or change in t, I get this, which pretty quickly becomes mass times acceleration, which is how we've always talked about Newton's second law. All right, let's talk more about that idea of impulse. All right, so we're going to start this talk about impulse out with a question, and I want you to keep it in the back of your head as we go and see if you can come up with a proper physics answer as we go, okay? So if you tripped and you fell, would it hurt more if you landed on grass or if you landed on pavement? Now, obviously, we know that the answer is pavement would hurt more, right? But why? Okay, now after this lesson, we should know, and I don't mean, answers like it's softer are easy to come up with, right? But from an actual physics standpoint, what's going on there? I mean, what does it even mean for something to be softer? Why does that hurt less? In both, you fell, right? So what's the difference? Okay, so keep that in the back of your mind and see if you can come up with an answer. But here we go. What is impulse? Well, to start talking about impulse, we have to first think about forces. So when a force is applied to an object for some time interval, we know that the object's motion is changed, right? Push something, you change its velocity. You change its motion. Now, the harder you push it, the more you will change the object's motion, right? Or the longer you push it, the more the object's motion will be changed, right? If you keep pushing and keep pushing and keep pushing, and you can get something going faster and faster and faster. Now, we now also know that changing an object's motion will also change its momentum, right? Because you're changing its velocity. And momentum is mass times velocity. So if this changes, the momentum changes. Now, we refer to this change in momentum as the impulse experienced by the object. That's all impulse is. It's how much the object's momentum changed by. Impulse is change in momentum. They literally mean the same thing. Why two different names for the same thing? Well, I mean, impulse is one of those concepts that was come up with in physics, and we talked about it a lot. And it's an important idea, so we kind of gave it its own name, right? But it is just the change in the object's momentum, okay? So let's take a look at the equations for impulse, aka the equations, how the different ways we can kind of calculate the change in momentum. So we can start from just the definition of impulse as being a change in momentum, right? As a change in momentum. Well, change in anything is final minus initial, right? And so final momentum is mass times your final velocity minus mass times your initial velocity. And then all we're doing here is pulling out the mass as a common factor, right? They both contain the mass, so we can pull it out as a common factor, leaving us with velocity final minus velocity initial, which is just the change in velocity. So the change in momentum is just the mass times the change in velocity, right? That's what impulse is. It's how much did your momentum change by? And we can calculate the change in momentum as mass times change in velocity, okay? We can also do it as we kind of just did by starting from Newton's second law as we learned it in Physics 20, right? The acceleration of an object is equal to the force acting on it divided by its mass. And acceleration is just change in velocity over change in time, right? So multiplying both sides by time and then multiplying both sides by mass, we get, again, this equation from our formula sheet. The force times the time is equal to the mass times the change in velocity, okay? An impulse is a change in momentum, okay? So how strong the force was times how long it was acting on the object will tell us how much the object's momentum will change by. And these all make sense, right? Look what happens to the change in momentum if we have a bigger force. Bigger force will cause our answer to be bigger here, right? If force goes up, the change in momentum goes up. Or if that force acts for a longer time, if time increases, change in momentum increases. You change the object's momentum more by pushing it harder and or by pushing it for longer. All right, now while impulse is a change in momentum, it's important to remember impulse and momentum are not the same thing, right? A change in your age of 5 years does not mean you are now 5 years old necessarily, unless you started from an age of 0, right? Changing your age by 5 years just means you got 5 years older. Okay, so similarly, a change in momentum and an impulse are not the same thing. This is how much the momentum changed by. This is just how much momentum it has. Okay, so to really get at this, right, an object experiences an impulse of 1 kilogram meter per second to the west versus an object has a momentum of 1 kilogram meter per second to the west. Let's think about that. What's the difference between these two statements? They're both valid, but they are very different. What is each one saying? Well, this one here is saying that the object's momentum has changed by 1 kilogram meter per second to the west, right? But there's a lot of ways that could have happened. It's just saying the difference between its new momentum and its old momentum is 1 kilogram meter per second to the west, right? So that could mean, it had 101 kilogram meters per second to the east, and now it has 100 kilogram meters per second of momentum to the east. That is a change of 1 kilogram meter per second to the west, right? 1 kilogram meter per second less east, right? That is an impulse of 1 kilogram meter per second to the west. Or it could have had no momentum initially, 0 kilogram meters per second, and it ended up with 1 whoops, that bracket doesn't belong there, ended up with 1 kilogram meter per second of momentum to the west. That is a change of 1 kilogram meter per second to the west in its momentum. That's an impulse of 1 kilogram meter per second to the west, right? I mean, it even could have been 100 to the west to 101 kilogram meters per second to the west. All of these changes are changes in momentum of 1 kilogram meter per second to the west. Just like, getting 5 years older, right? It could mean you went from being 10 years old to 15 years old, or 17 years old to 22 years old, or 100 years old to 105 years old. In all of those examples, the change in age was the same. It was 5 years, right? But that doesn't mean the actual initial and final ages were necessarily the same. Now, versus this one here, what is this one saying? Well, that one's just saying that the object's momentum is 1 kilogram meter per second to the west, right? It's not changing by 1 kilogram meter per second to the west. That's just its momentum, right? Not all these different possible ways in which it could have changed by that much. That's it, right? I mean, it's the difference between saying I am 5 years old versus saying my age has changed by 5 years, right? Okay, so be careful not to mix up impulse, a change in momentum, and momentum itself.
All right, and then this one here, getting us to think a little bit about units, right? So which of the following represents the units of impulse, or change in momentum, communicated in standard base units? So remember, the base units, there's a couple more that we'll learn in Physics 30, but for the most part, all the ones we've seen so far, they're kilograms, they're meters, and they're seconds, right? And then we have our derived units. Those are things like, for example, newtons. Remember, the equation for force, the main one anyway, is mass times acceleration. So in base units, mass is measured in kilograms, acceleration is measured in meters per second squared. But we use forces so often, we talk about them, so that we decided to just give them their own name. A kilogram meter per second squared, we kind of got sick of writing that, and we said, can we just call that a newton? So a newton is a standard unit, but it's not a base unit. It's what we call a derived unit, meaning that it's really a kilogram meter per second squared, but we give that the name newton, right? Another example is a joule. A joule is a derived unit. It is a standard unit, but if we really break it down, it's actually a kilogram meter squared per second squared, right? One equation that can show us that is, for example, the kinetic energy equation. It's mv squared over 2. So kilograms measure mass, right? And meters per second measure velocities. So when we square them, we get meters squared per second squared. Again, it is a standard unit. It's just not a base unit. Base unit only contains kilograms, meters, seconds. We'll later see in Physics 30 another base unit, an ampere, which is a unit of electric current. But that's for later. So let's go through these one at a time and see which ones represent impulse and which ones, if they do represent impulse, are they communicated in SI base units. So remembering that impulse is just a change in momentum, right? This is kind of the way of thinking about it as a change in momentum. It's also equivalent to a force times the time that force was applied for. Those are both valid ways to calculate the impulse. In fact, on your formula sheet, we use this, which is really just saying that a change in momentum is an impulse, right? They're both equivalent to the object's change in momentum, okay? So taking a look here, Newtons per second, newtons divided by seconds. Well, hang on a sec. That's not what we would get for impulse, right? We don't divide forces by times to get an impulse. So this actually fails both. This is not impulse. It's not base units either, right? It's using newtons. Those are a derived unit. That's not in terms of kilograms, meters, or seconds. Let's move on to this one. Newton seconds. So newtons times seconds. Would that give us the units of impulse? It would, right? Force measured in newtons times time measured in seconds. So this is actually a unit of impulse. It's one you'll see used sometimes, okay? So it is impulse. It is impulse. However, it's not base units. So it's not quite right for what we're looking for. Kilograms times meters per second squared. Well, no, that's a newton, right? That's mass times acceleration. That's not, mass times a change in velocity, right? Velocity is measured in meters per second. So no, this is not impulse. This also, it's not impulse, but it's in base units. So it does pass one of our tests, right? Kilograms, meters, and seconds. So process of elimination leads us to this one, but it's also, we can see it's correct, right? It's definitely in base units, just kilograms, meters, and seconds, okay? And it's a mass times a velocity, or a mass times a change in velocity, right? So this one's right. This is impulse, and it is base units. So that is the correct choice there. That is the units of impulse in base units. Makes sense. It's also the units of momentum, right? Well, impulse is just a change in momentum. So this is correct. This one is impulse. It's just not in base units. Nothing wrong with it at all. It's just not what the question asked for. Okay, let's try one where we actually calculate the impulse. All right, so we're asked to calculate the impulse, the change in momentum, right? That's what we're looking for. So change in momentum is what we need to find. Experienced by a 1,200 kilogram car, so that's its mass, entering a school zone and slowing from 50 kilometers per hour east, so that's the initial velocity, that's the speed it started with, to 30 kilometers per hour east. So that's its final velocity. That's the velocity it ends up with. Now, can we work with kilometers per hour and get units that we, can really work with, or at least that we want to work with for our impulse? No, right? Remember, we always want to work in our base standard units. So kilometers need to become meters, hours need to become seconds. So let's remind ourselves of how to do that conversion. We know that our initial velocity is 50 kilometers per hour. So we have to change two things here, right? We've got to change our kilometers into meters and then change our per hours into per seconds, okay? So let's just do them one at a time. We know that, well, if we did 50 kilometers per hour, that means we did 50,000 meters each hour, right? Because there are 1,000 meters in every single one of those 50 kilometers. So multiplying by 1,000 will give us, notice we'll have meters per hour. Makes sense. If we went 50 kilometers per hour, we went 50,000 meters per hour. But we don't want to know how far we went in a full hour. We just want 1 second, right? So now we need to convert those per hours into per seconds. And you can kind of reason here, right? We would divide by 3,600 because there's 3,600 seconds in an hour, right? 60 minutes, 60 seconds in every one of those minutes. So 60 seconds times 60 minutes gives us 3,600 seconds in an hour, right? And we want to end up with seconds on bottom. Hours will cancel out if I put them up here, right? Hours over hours, and 1 hour is the same as 3,600 seconds. Sure enough, right? It checks out with what we thought. We're going to divide by 3,600 because we don't want to know how far we went in a full hour, just in 1/3600th of an hour, right? AKA 1 second. Whoopsies, canceled out the wrong unit, hours over hours, and that ends up giving us 13.8889 meters per second. Okay, again, never round that. Keep your unrounded answer until it's the end and you're actually reporting your final answer to the correct number of sig digs. Okay, let's do the same for our final velocity. So same conversion, I just went ahead and did it there. Might be a good idea to pause the video and try converting it yourself, see if you get the same result, okay? But same conversion, so 30 kilometers per hour is equivalent to 8.333 meters per second. And now we're ready, right? We've got our final velocity, our initial velocity, we've got the mass. We can figure out how much this thing's momentum changed by, right? Because P equals mv. So if we take m times v final and subtract m times v initial, what we'll be finding is the change in momentum. Now, one very important thing we need to think about here, don't forget, it's a vector, right? We need to be thinking about direction. And when it comes time to do the math, that means we need to be assigning signs to certain directions. So I'm going to go ahead and call east positive, and therefore west is negative. Okay, so I'm going to say that, again, the change in momentum is just, I mean, there is this on your formula sheet, right? Mass times the change in velocity, but it makes a ton of sense too if we just go, you know, it's momentum final minus momentum initial. That's how you find the change in anything, final minus initial. And momentum final, well, P equals mv. So mv final minus momentum initial will be mv initial, right? And then if we pull out that common factor of m, we don't have to necessarily, but we could, just to make the calculation a little bit simpler, save us a few button presses on the calculator, right? There we go. And we've got all those numbers we're ready to plug in. So again, I'm calling east positive, so I'm going to make both of those velocities positive when I actually put them in here. And being careful not to mix up final and initial, right? So it's final minus initial. And our mass was 1,200 kilograms, so I'm going to do 1,200 kilograms times the change in velocity. And that gave me, let's just pause here for a second and make a prediction, okay? Which way was this car's impulse? Which way was its change in momentum? It was moving east. Now it's going slower to the east. So its initial momentum is to the east. Its final momentum is also to the east, but it's actually less, right? It lost eastward momentum, so to speak. So let's just see, what does that mean for the direction of the impulse? Make your prediction, and then let's calculate it out and see what we get. So if I do 1,200 times 8.333 minus 13.8889, I get negative 6,666.67. We could see our units would be kilograms times meters per second. Okay, so that negative, what does that mean? It means the impulse was to the west, right? We called east positive. So getting a negative answer just means in the opposite direction of whatever we called positive. So this is a westward impulse, right? This car's change in momentum was to two significant digits, 6.7 times 10 to the power of 3 kilogram meters per second to the west. So sometimes students don't like that. They say, but it was moving east, right? True, but we're not talking about which way it was moving necessarily. We're talking about how its momentum changed, right? And it got, you know, less east is the same as more to the west, right? Its impulse was to the west. It had a westward change in its momentum, okay? It had a lot more momentum to the east to start out with than it did at the end. So this is a westward impulse. Its momentum changed to the west by that amount, meaning that it lost some of its eastward momentum, okay? So again, doesn't mean that the momentum was to the west, right? We know its momentum was actually always to the east, right? Its momentum was not negative, but the change in momentum was negative and to the west, right? Like going from positive 10 to 5 is a change of negative 5, right? That's subtracting 5. Going from negative 5 to negative 10 is also a change of negative 5, right? So the impulse here was negative and to the west, even though its momentum was always to the east. It just got less to the east. So still a negative change. Okay, let's look at this one here. A student states that a 1,200 kilogram car, so same mass as the car we just talked about, traveling the opposite direction and speeding up from 30 kilometers per hour west to 50 kilometers per hour west as it leaves the school zone would experience the exact same impulse as the above car. Do you agree? Well, let's just think about this. What was the car's change in velocity, right? It was from 50 east to 30 east. So that's a change of, we could say, negative 20 kilometers per hour,
right? Or 20 kilometers per hour changing in the west direction, right? Less east is more west, okay? Well, this car went from 30 west to 50 west. So that's a change in velocity of 30 kilometers per hour to the west, right? It's increasing its westward velocity. This one was decreasing its eastward velocity. So it has the same mass. It went through the same change in velocity. It's going to experience the exact same change in momentum, the exact same impulse. So yes, I do agree with this student just by kind of thinking about it. But if you don't believe me, let's calculate. So I've set it up here, right? 30 kilometers per hour to the west is its initial velocity. We know that 30 kilometers per hour is 8.333 meters per second, okay? Only difference here now is VI is 30 and it's to the west. V final is 50 kilometers per hour to the west, okay? Now, I'm going to stick with my same direction convention. I'm going to call east positive and west negative. Again, keep in mind, we could switch it. It just means if I make west negative, or west positive, then east has to be negative, and the meaning of the sign switches around, right? But if we look here, okay, so our initial velocity is going to be positive 8.33. Our initial velocity is now going to be negative 8.333 because we're calling west negative, and our final will be negative 13.8889. So it's the same formula, same calculation. Let's figure out this car's change in momentum, its impulse. So its mass is 1,200 kilograms. The final velocity is now negative 13.889 meters per second minus the initial velocity. We're defining west as negative, so we're subtracting negative 8.3333 meters per second. So subtract those and then multiply by 1,200. We're going to do negative 13.8889 minus negative 8.3333. So minusing a negative gives us a plus. So 1,200 kilograms. This comes out to be negative 5.5559 meters per second once you subtract those two. And sure enough, our impulse is negative 6666.67 kilogram meters per second, right? So to two significant digits. And remember, we have to interpret that negative. It's not good enough to just leave it as negative if we know what the negative means. The negative means to the west. So it's 6.7 times 10 to the 3 kilogram meters per second to the west. So look at that. Sure enough, they are the exact same, right? Which makes sense because the change in velocity for both of them was 20 kilometers per hour in the westward direction, right? Here, that meant it was moving east and getting slower. Here, that meant it was moving west and getting faster. But either way, it's the same change in velocity in terms of the magnitude and direction. And so the change in momentum is the same, right? The momenta are definitely not the same, right? This has a very different initial final momentum than this one, right? But the change in momentum was still the same. It's a bit like, if you're 15 years old and you become 20, that's a change in age of 5 years, right? If you're 80 years old and you become 85, that's a change in age of 5 years. Very different initials and finals, right? But still the same change. So same idea here. The same impulse. Okay, let's try this one out. So it asks us, what impulse has the ball above experienced? Let's just take a look at what's happening. We've got a ball coming in, moving to the right. Looks like it's going to bounce off of this wall, right? Before it's headed towards the wall. After, it looks like it's bounced off the wall and it's returning the other way. So it tells us that, before its velocity is just, we're calling it initial velocity, right? We don't actually have a number, but it's VI, right? And after, its velocity is negative VI, meaning that it's the same size, same magnitude, it's just now in the opposite direction. So it's moving just as fast, but it's moving the opposite direction. Okay, so we want to know the impulse, the change in momentum, right? Well, impulse is, like I said, right? Well, change in momentum. Momentum final minus momentum initial. So it's mass times the change in velocity. Okay, now we don't have any numbers here, but we can get an idea for, in terms of the variables we have, what the impulse would be.
So the change in momentum is just mass times velocity final minus velocity initial, okay? And what's our final velocity? Well, they're saying it's just the same size as velocity initial, but opposite direction. So same magnitude, opposite direction, same number, opposite sign, that means when it comes time to actually do the math with it. So that means our change in momentum is the mass of the ball times v final, yes, but we know that v final is just negative v initial. So v final is negative v initial minus v initial, and look at this. That means our impulse, our change in momentum, is just mass times, well, negative vi minus another negative vi, minus another vi, that's negative 2 vi, right? Just combining like terms there. Negative 1 vi minus 1 vi is negative 2 vi. And so the change in the ball's momentum, the impulse that it's experienced, just pulling out that negative 2, is going to be negative 2 m v initial, which you might notice is that's just its initial momentum. So its initial momentum, the change that it's experienced is negative 2 mvi, right? Because the change in velocity was negative 2 vi. Sometimes students don't like this one. They say, shouldn't it be the change in velocity be 0? Because vi and negative vi just make 0. But we don't add, we subtract, right? One way I've found that helps visualize this is that look at it this way, right? What change in velocity did it go through? It went through a change in velocity of negative 2 vi's, right? Graphing it out, v as a function of time, right? It had a velocity of positive vi. Then it hits the wall and it rebounds with a velocity of negative vi. So now its new velocity is negative vi. Well, ask yourself, what's the change in velocity that occurred then, right? To go from vi to 0, well, that's a change of negative vi, right? That's its change in velocity there. But then to go from 0 to negative vi, that's a change in velocity of another negative vi, right? Vi to 0 is negative vi. 0 to negative vi is another negative vi. So overall, what was its change in velocity? It was negative 2 vi, right? And therefore, its impulse, the change in momentum, was the mass times that. Ooh, a graphical analysis one. Let's give it a shot. So the graph below depicts velocity as a function of time for a car. So this is showing us how the car's velocity changed as time went on. Determine the impulse experienced by the car during the first 9 seconds if it has a mass of 1,800 kilograms. Okay, so that's its mass. Now, it happened during the first 9 seconds. So let's just think about this. Let's let the equation tell us what to do, right? Now, graphical analysis, like I said, it's always about slope, area, intercept. Sometimes, though, it's even just about like reading the numbers we need off of the graph, okay? So the impulse, the change in momentum, we know that that is just mass times the change in velocity, right? Okay, well, what this graph is showing us is the velocity of the car as time goes on. So we can just read its final velocity and read its initial velocity and actually get what we need for this question, okay? So after 9 seconds, it looks like at 9 seconds, the car was moving at, okay, this is 10, this is 20, so it looks like it's going up by 2s, right? 10, 12, 14, 16, 18, 20. So the final velocity looks like it's 18 meters per second. Now the initial velocity, right, when time was 0, okay, here's 9 seconds. So when time was 0, it looks like the initial velocity was negative 12. Careful, these are scaled by 2, not by 1. Time axis is scaled by 1, so 5, 6, 7, 8, 9 seconds. The initial velocity looks like it was negative 12 meters per second. In this case, we don't actually know what that negative means, so we'll just have to say negative 12. It didn't tell us what the positive or negative directions were, okay? So thinking about what this car was doing, it was going pretty fast in the negative direction. Then it actually got slower and slower and slower, right? So maybe it was moving west, let's say, and then got slower and slower and slower. See how its velocity is getting closer to 0? That means it's slowing down. But then it kept accelerating to the west, and now it's actually kept accelerating to the east, and now it's actually moving in the positive direction, getting faster and faster, right? So it was moving in the negative direction, got slower, 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 briefly stopped, and then got faster and faster and faster, but in the positive direction. Then moved at a constant speed, then slowed down to a stop, okay? Either way, though, our final velocity is positive 18, our initial velocity is negative 12, and we were told that the mass of the car is 1,800 kilograms. So final velocity, positive 18 meters per second, minus initial velocity, negative 12 meters per second. And we get that. The impulse experienced by the car is 54,000 kilogram meters per second. Okay, now again, they didn't tell us what the positive or negative directions were, so the best we can do is just have the correct sign here based on how they've set it up. And to two significant digits, that would be 5.4 times 10 to the 4 kilogram meters per second. Okay, so again, graphical analysis, the graph contained the information we needed. Told us the initial velocity, told us the velocity after 9 seconds, so that let us use our equation here, okay? So when I said graphical analysis is always about slope, area, intercept, this is sort of like intercept, right? It's reading the correct values off of the graph. It's just not quite the same as actually an X or Y intercept, but same idea, reading the appropriate value off. Okay, let's talk about the relationship between force and time and how they both relate to impulse. So let's just think about something before we jump into that notes example there. Okay, I want you to imagine two different scenarios. The first one, you're going to be driving in your car 50 kilometers per hour and you see a red light way up ahead, but like you're going to have to stop for the red light. Okay, and then in the other scenario, you're also driving 50 kilometers per hour, and then in front of you, a cat runs out into the road and you've got to stop very quickly. Okay, the cat is safe, don't worry, but slightly different situations, right? In one, you got a lot of time to stop. You see the red light way up ahead. In the other, you got to slam on the brakes really quick because the cat's right in front of you, okay? Now, let's just compare some physical quantities here. Your mass in the two situations, it's the same mass, right? It's the mass of the car. So mass is the same either way, okay? Also, in both, you're initially driving 50 kilometers per hour. So your velocity initial is the same either way. Now, your final velocity, in both situations, you're going to come to a stop, right? So in both, your final velocity is 0. So it's the same. You come to a stop in both situations. Now, putting those ideas together, if the mass is the same and the final velocity and the initial velocity are the same between these two scenarios, well, the impulse has to be the same too, right? Initial momentum would be mass times VI. Well, those are the same in these two situations, mass and VI, right? The final momentum would be mass times V final. In both scenarios, the V final is 0. So the change in momentum has to be the same because the initial momentum and the final momentum will be the same. Mass is the same, initial velocity is the same, and final velocity is the same. So the impulse in both situations is the same. What is different now, though, is how that impulse was achieved, right? Because we know that a force applied for a certain amount of time will change something's momentum. It will cause an impulse, okay? But in this situation, you had a lot of time, right? So you had a large amount of time versus when the cat ran out in front of the road, you had to cause that impulse very quickly. So you had a very small amount of time to achieve that impulse in the cat scenario, okay? So because there was such a large time, for this scenario, do you slam on the brakes as hard as you can when you see a red light way up ahead? No, right? You can apply a small force for a longer time, okay? And for the cat situation, you have to stop very quickly, so you need a very large force, right? Again, the impulse is the same either way. It has to be. All the things that go into calculating the change in momentum are the same, right? But this one was caused with a very small force, just applied for a longer amount of time. This one had to be a much shorter time to achieve the impulse, and so the force had to be much larger to cause that impulse more quickly. And that is the key relationship between force, time, and impulse. So looking at this truck here, it's a very similar idea, right? Consider the effect of the stopping time, or the, change in impulse time, on the force that's required. Here we have two trucks. Both are traveling at the same speed initially, and both end up stopped. So they go through the same change in velocity, they have the same mass, so they experience the same impulse, right? So what's the same for the two trucks? Their change in momentum, right? Their impulse. They had the same mass, they went through the same change in velocity, they both had the same initial and the same final, okay? And so their momentum did change by the same amount in both scenarios. What's different is how that impulse was achieved. For this truck, right, the impulse was achieved very quickly with a very large force, right? And so the driver is going to feel that. That is going to hurt more, right? Forces are what hurt us, okay? So large force to stop in a short amount of time. Large force and a small time for the, I'll call it the wall truck, because it just drove into the wall, right? Whereas for this one, right, longer time, this comes into contact with the hay earlier, and so it's applying that force that's slowing it down the whole time it's moving through the hay, and so it gets slowed down over a longer time period, meaning that the force can be smaller, right? And you're not dealing with forces that can actually damage your truck or injure you. So smaller force, longer time for the hay truck. And this is actually the idea behind almost all like safety equipment, right? That's in a car or in anything, really. I mean, if you think about, airbags, what does an airbag do? Well, an airbag is there to come out and meet your face as it's coming forward, so that it starts applying the force earlier, giving you, a longer time to eventually come to a stop, right? So that the force acting on you can be smaller, because a force is what's going to injure you, right? A large force is what's going to hurt you. So that force spread out over a longer time, either way, the impulse is the same. You were moving at some speed and you're going to have to come to a stop, right? Now that hurts a lot less because the force is a lot smaller if you can do it over a longer time period. Smaller force can cause the same impulse but in longer times, okay? Compare that to, instead of the airbag, if you just hit the solid steering wheel, you're coming to a stop basically instantly. The steering wheel has no give, right? So you achieve that impulse in a very short amount of time, which means there's a very large force exerted on you, right? So if we return to this question that we started out this section on impulse in, okay, would it hurt more if you fell on grass or pavement? We know the answer is grass, but now we can say, it would hurt less on grass, it would hurt more on pavement. Now we can say why, right? The grass is taller and it has more give. So we start contacting the grass earlier, right? And that force that's being applied to us to stop us can be smaller because it takes a longer time to bring us to a stop, right? It's the same idea as, even like a helmet in football, right? It gives some cushion, but the idea of that cushion is that so you don't, when you run into another player, you're not immediately stopping, you're kind of moving through that cushioning. And so longer times allow smaller forces to be acting on you. Either way, though, the impulse is the same, right? We can go from driving 100 kilometers per hour to 0 kilometers per hour and be just fine if we brake slowly and apply a small force over a long time. The force acting on us is never that big. If we drive straight into a wall and come to an immediate stop at 100 kilometers per hour, that requires a very big force, and therefore we would be, injured in that situation. Okay, and so the impulse is the same either way. Final velocity, initial velocity the same, mass the same. It's just how was that impulse achieved? Large, dangerous force over a short time, or smaller, safer force, but for a longer time. Okay, let's try out an example here where we'll see that in action, one having to do with airbags. So A 1,200 kilogram car is traveling at 100 kilometers per hour when it hits a tree. The driver, 62 kilograms, is stopped by an airbag in 90 milliseconds. The passenger, 64 kilograms, is stopped by the dashboard in 10 milliseconds. So let's pause right there. Pop quiz. Who's going to feel a larger force? The passenger or the driver? The passenger, right? They stopped in a shorter amount of time. To achieve the same impulse in a shorter amount of time, you need a larger force. So that passenger is going to be experiencing a larger force. And if either of them is going to be injured, it's going to be the passenger before the driver, right? They're experiencing a larger force acting on them. So it wants us to calculate the force in both cases to see why, why we use airbags. Why are they so important? So we want to calculate the force, okay? We're given the mass of each object, and we're also given their initial velocity. So let's look at it like this. We know the equation we have here is that a force times a time is equal to a mass times the change in velocity, right? So to calculate the force here, divide both sides by the change in time. And we get, this is actually just Newton's second law, right? The force is equal to the mass times the acceleration. Change in velocity over change in time, that's just the acceleration. All right, so let's start with the driver. Let's calculate the force that was acting on them, okay? So their mass was 62 kilograms. Their initial velocity was 100 kilometers per hour. They were moving with the car, right? And so I've gone ahead and converted that into meters per second, multiply by 1,000, divide by 3,600. They didn't tell us the final velocity, but can we figure it out here, right? They hit the car, they hit the tree. They came to a stop, right? Stopped. So our final velocity is actually just 0 meters per second. So let's go ahead and calculate the force acting on the driver. We know that the force will be equal to the mass times the change in velocity, and change in velocity is just final velocity minus initial velocity over the time that went by. So the force acting on them will be 62 kilograms times 0 meters per second minus 27.778, right? That's final minus initial over the time. Now be careful, the time is 90 milliseconds. So that's 90 times 10 to the minus 3, right? Or 0.09. I'm just going to do it as 90 times 10 to the minus 3 seconds. Nothing wrong with that. Just a reminder, the prefixes are all on the back of your formula sheet there, right? So we had a little m, it was ms, milliseconds, and it tells us that milli, little m, means 10 to the negative 3, if you ever forget any of them, right? Like kilo, we know that means 1,000. Kilo has the symbol K, 10 to the 3, 1,000, right? Okay, so back to this one. Our driver, when I calculate that all out, I get that the driver, I'll just put a little d for driver there, the force they experienced was negative 1.91 times 10 to the 4 newtons, or about 19,100 newtons, okay? Now, if you're thrown off by that negative, that actually makes sense, because when I called my initial velocity positive 27 meters per second, I actually did. I defined the initial velocity direction as positive, right? And this force brought them to a stop. So if they were moving forwards, they need a backwards force to stop them, right? The force is obviously in the opposite direction they were moving in order to stop them. So that's the force acting on the driver. Let's do the passenger. So for the passenger, right, the mass, the initial velocity, and the final velocity are all the same as they were for the driver, right? So the impulse they experience, their change in momentum, is going to be the same. What's different, though, is the time it took, and therefore the force that the passenger is going to feel. So the passenger has a slightly larger mass, 64 kilograms. Their final velocity is 0. Their initial velocity is 27.7778 meters per second. 100 kilometers per hour, but the time it took them to stop was only 10 milliseconds. So they only took 10 times 10 to the minus 3 seconds to come to a stop. So putting those numbers into my calculator, I got that the passenger actually experiences a force of negative 1.8 times 10 to the 5 newtons. Okay, so they're experiencing about 180,000 newtons of force, while the driver was only experiencing about 19,000 newtons of force. Now, obviously, neither of them are going to, feel great after this, but the passenger is experiencing they're experiencing 9 times more force than the driver, right? Because they came to a stop 9 times faster, right? So 9 times more force is a very significant factor here. Okay, that's quite a bit more force, 180,000 versus about 19,000 newtons of force. So this is the idea behind airbags, seatbelts, tons of safety devices. It's to make it so that it takes longer for you to stop so that you can be stopped with a smaller force, right? I mean, it's even the same idea if you're to jump off of a table or something and land, right? How do you land? You kind of cushion yourself with your knees so that you can make that stopping time longer, and therefore the force that's acting on you smaller and not hurt as much, right? If you imagine locking your knees and jumping off the table, that's probably going to hurt a bit because you're coming to a stop almost immediately, and that requires a big force. Okay, here's some that were from a released diploma. So these are real questions that were actually written by Alberta students in Physics 30 when they wrote their diploma exam. Let's see if we can try these out. So as a child catches a ball, he exerts a force, F, on the moving ball for a time interval, delta t. The mass of the ball is 250 grams, okay, and its velocity changes from positive 5 meters per second to positive 1 meter per second as a result of the force. So he's catching the ball, meaning he's slowing the ball down. Okay, so the first one up asks us, what is the magnitude of the impulse that the child applies to the ball? So remember, magnitude just means the size. In other words, we're going to find it like we always would, but they're not worried about giving a direction in our final answer. Okay, well, only one formula. Impulse is just one thing. It's the change in momentum, right? So sometimes we get that with force times time. Sometimes we get it with mass times change in velocity. In this case, we have the change in velocity and we have the mass, right? So let's go with that one. Mass times change in velocity. So the impulse will be mass times, change in velocity. Final velocity minus initial velocity. So what is our mass? It's 250 grams. Be very careful though. 250 grams. We don't work in grams in physics. We work in kilograms. So 250 grams, there are 1,000. Whoops, got that backwards. There are 1,000 grams in 1 kilogram, sorry. So we need to divide by 1,000, right? We can tell we don't even have 1 kilogram. So we can tell we need to divide, get a smaller answer, right? And we can confirm that our units are canceling out correctly. Grams over grams will leave us with kilograms. So this is 0.250 kilograms. Makes sense. If 1,000 grams is 1 kilogram, then 250 grams is only 0.25 kilograms. So here we go, 0.25 kilograms times our final velocity. So always read carefully, right? From 5 to 1. So this is where it ended up. That's V final, this is V initial. So 1 meter per second minus 5 meters per second. And therefore our change in momentum, our impulse is 0.25 times -4. That gives us -1 kilogram meters per second. Okay, or we know also that impulse can be measured as Newton second. Look like that what they chose to use here. A Newton second and a kilogram meter per second are the same thing. I'll prove that in a second here, but it looks like our impulse is -1 kilogram meter per second, or 1 Newton second, or -1 Newton second, but it said magnitude, so we're just not worried about that negative in our final answer. So notice here, do you know how you get this answer? You get this answer from forgetting to convert grams to kilograms, right? So they base the wrong answers on common mistakes, okay? So the answer is A. I'm just going to quickly show you. A Newton second is actually the same thing as a kilogram meter per second. Don't believe me? Good. Why should you take my word for it? But remember, a Newton, since force equals mass times acceleration, a Newton is a kilogram meter per second squared. So A newton times a second is a kilogram meter per second squared times a second. And a second divided by a second squared, right? Well, the second can cancel out here. And one of those seconds in the second squared, maybe I'll just really show this here. Seconds squared means seconds times seconds, right? So if I multiply that by seconds, one of the seconds cancels out in the denominator. The seconds in the numerator cancels out, leaving us with, sure enough, kilogram meters per second. Right? So a Newton second is the same thing as a kilogram meter per second. We use them interchangeably. Newton second is often used more commonly for impulse, especially when we're talking about forces and times, right? But at the end of the day, it's the same thing. It's a change in momentum. All right, let's look at number 2. Same information, but new question. So number 2 asks us, if when catching the ball, the child had applied triple the force, so 3 times as much force, then the length of time that it would have taken to slow the ball down would have been 9 times as long, 3 times as long, 1/3 as long, or 1/9 as long, right? Right off the bat, do A and B make much sense? If we apply a bigger force, should it take longer to slow the object down? Not really, right? So we're not expecting those to be the answer, right? If you push something harder, you change its velocity more quickly, not less quickly. But let's try this out. We know what equation can tell us this. Well, we know that impulse is also force times time, right? Now the impulse is the same either way because it's saying how long would it have taken to slow the ball this amount, right? So still the same impulse. If we applied triple the force, just going to leave a little room here so we can think about the numbers that go in. If we triple the force, what would happen to the time? So that the impulse stayed the same. Right now, I've multiplied this side by 3, right? If the impulse needs to be the same, I need to multiply the time by 1/3. So that overall, we haven't actually changed the overall impulse, right? Yes, the force got 3 times bigger, but as a result, the time will now be 3 times smaller, or 1/3 as large. So the answer is C, right? D is just trying to get us if we thought it was squared for some reason, right? Another way to look at it, if impulse is force times time, we isolate for time to see what happens to it. Well, look, if I multiply the force by 3, right? Time used to be this impulse over the force. If the force gets 3 times larger, look what's happening to our answer, right? We're now dividing it by 3. We're dividing it by something that's 3 times bigger. Almost look at it as we divided that side by 3, so time is going to get divided by 3 as well to keep both sides equal. So it would take 1/3 the amount of time if we applied a force that was 3 times larger. Okay, one more here. So if when catching the ball, the child had applied a smaller force, then the impulse experienced by the ball would be blank and have a blank stopping time. Whoops. Looks like I missed an I when I was copying that one over from the diploma. So in the first blank here, we're going to say whether the impulse was either smaller or the same. And then we'll say whether it has a shorter or a longer stopping time. Now, this is where a lot of students get tricked, right? They think, okay, bigger force, that must cause a bigger impulse, right? But again, think back to the example with the cat and the stop sign, right? Either way, you're changing your momentum by the same amount. Either way, to catch the ball, the child is slowing it from 5 meters per second to 1 meter per second. So the impulse is the same, right? Sorry, I said bigger force, but this is actually a smaller force, right? But same idea holds, right? It's not a smaller impulse, it's just achieved with a smaller force. So A and B we can eliminate. Now we need to decide, would it have a longer stopping time though, or a shorter stopping time? Well, if you use a smaller force to achieve the same impulse, it's just going to take you longer, right? Not shorter. You need a bigger force to make it come to a stop in a shorter amount of time. That's what we did in number 2 there. So the answer is D, right? This is like the stop sign situation. You've got a longer time to stop it, and so you can use a smaller force, right? Same idea. A smaller force to cause the same impulse will require a longer time to do it.
Okay, so that would be option D. So look at that. On the diploma, 3 questions, really just coming down to that force-time relationship. I guess not number 1 isn't really about that force-time relationship, but 2 and 3 are. Okay, so impulse was the same either way because the change in momentum was the same because the change in velocity and the mass were the same, right? It's just big force versus small time or small force with a large time. Okay, one more. Oh, sorry, before we do that last diploma example, time to pause the video, try out a couple practice questions. At the very least, try out this one. Of course, the solutions are always posted in the Google Classroom. The answers are in the textbook if you don't want, the full solution, but you just want to know if you got it right. I also put the answers directly in here as well, okay? So take the time to at least try that one out, but feel free to try a couple more that are nearby it because you can probably do those as well. Take a little break from my voice, and when you come back, we'll talk about graphical analysis with impulse and force time graphs. We'll do that actually using a release diploma question as well. All right, so try that one out at least, and come on back when you're done. All right, so here is one from the diploma. It is a graphical analysis question. They've drawn the line of best fit for us. That's nice. They don't always do that, but they did here, okay? But let's just take a look at the graph and then get on to the question here. It says the physical significance of the area under the line of best fit from t equals 0.04 seconds to t equals 0.86 seconds is, our options are impulse, work, momentum, or change in impulse. Okay, well, what does area mean, right? What are we doing with the y and x variables if we're finding the area? Remember, finding an area is about multiplying 2 dimensions together. If we were in math and I asked you what is the area of that square, you would say it's y times x, right? So it's the same idea here, except we're being asked what happens if we multiply force by time, because that's calculating the area under this graph, right? So area equals y times x, and on this graph, that means we're doing force times the amount of time that's gone by. So force times time. Do we have an equation for that? What does it represent? Right? We could go to our formula sheet if we're not sure, but force times time, that is the change in momentum, right? We have this formula, mv equals force times time, right? Both are impulse, both are the change in momentum that's happened, okay? So not the work, definitely not quite the momentum, right? And not the change in impulse either. That's a change in momentum, right? What this is the impulse, the change in momentum. F times t, area, y times x, is the impulse. Now in number 2 here, it asks us to actually calculate it. So we've worked out that we need to find the area to get the impulse. Now it's saying figure out the impulse using graphical analysis. So the magnitude of the impulse that the object experiences, the magnitude of the impulse of the object that experiences the force from 0.04 seconds to 0.86 seconds is, we've already established this, right? We need to find the area of that graph. So force times time is y times x, meaning we are finding the area. So let's go ahead and do that. All right, so we want from 0.04 seconds. So let's just take a look here. Looks like we're going up by 0.02, right? 0.02, 04, 06, 08, 0.1. So this x-intercept here actually looks like where we're going to start finding our area up to 0.86. So here's 0.8, 0.82, 0.84, 0.86. So that's our starting point. So be careful. We don't always want the full area, right? We just want to know the impulse up until this time of 0.86 seconds. Okay, and again, this kind of makes sense. The force is not constant. We're actually pushing this thing harder and harder and harder, right? So we know that a force times a time gives us the impulse. What we're essentially doing here is, force times time, force times time, force times time, force times time, recalculating it over and over again. And we realize that by doing that, we're actually just finding the area of this triangle, okay? What we're actually doing is integral calculus. We're just kind of breaking it down a bit more. So from 0.86, let's just figure out exactly the area we're looking for here, okay? We want to figure out the area of this
triangle, right? And it's actually kind of a remarkably simple solution to what could seem to be a very complicated problem, right? We know forces cause changes in momentum. They cause an impulse to occur, but this force is actually constantly changing. Kind of makes your head spin, right? Every time you're pushing it harder and harder and harder, so you're causing an impulse, but every second you're causing a different impulse than you did in the previous second, right? And the remarkably simple solution to that is that we end up just finding the area of this triangle, right? Again, it kind of makes sense if we applied a constant force of 3 newtons for, that amount of time, we'd have no problem saying the impulse would be 3 newtons times the amount of time that went by, right? But here, for most of it, we were actually pushing less than 3 newtons, right? We were actually pushing less hard. And so the result is, instead of finding the area of this rectangle, right, which would just be length times width, we're going to find the area of this triangle, length times width divided by 2, right? And so that remarkably simple adjustment to divide by 2, because we're finding the area of a triangle, accounts for the fact that for most of this, we were actually pushing less hard than we were at the end here. Okay, so let's actually go ahead and do it now. Let's figure out the area. So we know for a triangle, the area is going to be base times height divided by 2. So what is the height of this triangle? Well, looks like it's, about 3.5 newtons. Not about, it's pretty precisely at 3.5 newtons, right? Halfway between 3 and 4. So 3.5 newtons, okay? Minus 0 newtons if you like, but we can see that it's just 3.5 newtons. Now for our change in time here, on the x-axis, the base of this triangle, the base, which is just our change in time, makes sense, right? The amount of time that went by along our x-axis here. Be careful, it's not 0.86, right? Because we didn't start this at 0.0. So it's 0.86 minus 0.04, right? Final minus initial, to figure out how much time actually went by. So that's 0.82 seconds. So we're going to take our base times our height divided by 2, because we're finding the area of this triangle. So that gives us, our base was 0.82 seconds. Our height was 3.5 newtons. And then divided by 2, I got 1.435 Newton seconds. Okay, now typically these numerical response on the diploma, they would tell you how many significant digits for a graphical analysis one, because the rules on graphical SIGDIGs when we're doing graphs can be kind of iffy, just because of the fact that we don't know, like, is this, 0.80 or is it really just 0.8? And we don't know the 100th place, okay? So the short answer is it will tell you. I'm just going to say, let's go to the same precision given here, which is to the 100th place. So 1.44 Newton seconds. Okay, I think on this original diploma it actually said to the nearest 10th. But I'll go ahead and say 1.44, mostly just because that's also what will fit in our box here. So if this were the diploma, when we go to answer and fill in our Scantron, we would say 1.44. So we'd fill in the 1. You do fill in the decimal. The decimal gets a spot. 1.44, right? So all we did there, we used the formula. Impulse is force times time, right? Our graph has force on the y-axis, time on the x-axis. So y times x, that's an area. So find the area of this triangle, and you are finding the impulse for the object during that time. Okay, 2 more also based on this graph. So now it's asking us if the mass of the object was 0.5 kilograms, and it started from rest. So it's saying initial velocity was 0. Then the object's final speed at the end of the 0.86 seconds would be blank meters per second. So we're just looking for VF. Well, we've just found its change in momentum, right? We found its change in momentum. So we know that the change in momentum is, going to use the unrounded, 1.435 Newton seconds, or kilograms meters per second, okay? And we know that the impulse, or the change in momentum, is, well, mass times the change in velocity. So we know the mass, they just told us it's 0.5 kilograms. We know the initial velocity, they told us it started from rest, so the initial velocity is 0. And we know the impulse. The only thing we don't know here is the thing we want to find, v final. So this is a totally solvable equation, okay? What's more, our initial velocity is 0, so we can even just, get rid of it there. And that shows us that the change in momentum will just be equal to the mass times the final velocity, right? Vf minus 0 is Vf. And so now just divide both sides by the mass, and we get that the object's final velocity will just be the impulse, change in momentum, divided by its mass. So I'm getting that the final velocity will be 1.435 Newton seconds divided by a mass of 0.5 kilograms. And that gave me 2.87 meters per second. If you're wondering, how did you get meters per second as the units? Remember, this could also be measured in kilogram meters per second. That's one way to look at it. So kilogram meters per second over kilograms, of course, leaves us with meters per second. But also, don't forget, a Newton second is really, a Newton is a kilogram meter per second squared, because force equals mass times acceleration, right? So if I take times another second, right? So if I take a kilogram meter per second squared times a second, and I divide it by a kilogram, like we were doing in this equation here, right? We can see our kilograms would cancel out, and then seconds and seconds squareds, one of them would cancel out, leaving us with meters per second. So the units have our back. Looks like we did something right. So to fill that one in, we would say 2.87, and we would fill out 2.87. If you're looking at the filled in notes from before, you might be noticing that I got something slightly different. I think honestly when I filled those out the first time, I was using what the diploma said for what to round to the nearest blank, and I didn't I didn't encounter that here. I didn't have it put into the notes for some reason here when I copied them over. So apologies if that's confusing, but nothing wrong with how we're doing it here either. Based on what they said, they didn't tell us what to round to, and for graphical analysis, the rules are a bit different. So I think that's totally fine there. And last one here. It's actually a very similar one. The only difference is they're changing the initial velocity from being rest to being 4.5 meters per second south. Okay, so the mass of the toy car experiencing the force described by the graph on the previous page is 5 kilograms. Okay, I guess they changed the mass as well. So now our mass is 5 kilograms. It has an initial velocity of 4.5 meters per second south. So I'm going to call south negative, just because that's typically what we would do. South negative, north positive, okay? And the direction of the force is south, so the force is to the south as well. Okay, now that's an important detail. The force is to the south as well. So the impulse being experienced here is in the same direction as the initial velocity, okay? The force is to the south, so it's going to cause a delta P to the south as well, right? If we push something to the south, we change its momentum to the south. So that's going to help us decide on the sign that we give the impulse. So the final velocity of the car is what we want to know. We know that the impulse, we already calculated the impulse using the graph, right? The impulse is 1.435 Newton seconds or kilograms meters per second, okay? However, which direction is that impulse? It's to the south, right? If we push it to the south, we change the momentum to the south. So that's an important detail there, okay? We had to be on our toes for that, because it will change our final answer, right? You can see here 2 options where it got slower, 2 options where it got faster. We know, if we read carefully, that it should be getting faster because it's moving to the south and we're also pushing it to the south. So we're going to change its velocity to be more south, right? In fact, without even calculating, I could tell you right now that the only answer that even makes sense is D, right?
it definitely won't be moving north. The force was to the south and it was already moving south. So there's no way we could have stopped it and turned it around so it's moving north. And if it was moving south and we pushed it south, it should have gotten faster to the south, not slower to the south. So even without calculating, I'm feeling pretty good about D, but let's go ahead and calculate and make extra sure. So we know that the impulse is equal to the mass times the final velocity minus the initial velocity. Okay, let's go ahead and start solving this for the final velocity. That's what we want. It's inside those brackets, so before we do anything in the brackets, we got to deal with everything outside of the brackets, right? Reverse order of operations when manipulating. We're undoing the things happening to VF. So before we get in those brackets, we got to deal with everything outside of the brackets. Being multiplied by mass, so let's divide by mass to undo that. We'll get that V final minus V initial equals the change in momentum divided by the mass. And now we got rid of everything outside of the brackets. We can move into those brackets. We're subtracting VI from VF. To undo that, the opposite would be to add the initial velocity to both sides. So we get that the final velocity will be the change in momentum over the mass plus the initial velocity. Okay, now subbing in, being careful to remember our directions. We called south negative. So anytime I put in a vector that's to the south, I need to make sure it's negative. If there were vectors here that were to the north, I would make them positive, but we don't have any of those. So negative 1.435 kilogram meters per second is our impulse. Mass is a scalar. Mass can't have a sign, so 5 kilograms. Plus our initial velocity, but our initial velocity is 4.5 meters to the south. Sorry, 4.5 meters per second to the south, so I'm going to make it negative 4.50 meters per second. So dividing these, I got negative 0.287 meters per second, okay? And then minus 4.50 meters per second. I got that the final velocity was negative 4.787 meters per second. Okay, now our negative, what does that mean? Well, we defined south as negative for this one, right? So our final velocity would be to 2 significant digits, and I am going to worry about the sig digs here because we did just use this initial velocity to 3 sig digs that they gave us. So our final velocity would be 4.79 meters per second to the south. Reminder, we don't say the negative and the south, right? Negative is like the placeholder that we use while we're doing the math so that we can give opposite directions, opposite signs. But really, the negative just meant south for us, right? We don't want to say negative south. Negative south would actually mean north. Negative kind of means opposite, right? So negative south is actually north. We don't want both of them. So our final velocity is 4.79 meters per second to the south. Hey, look at that. That's the only one that we said made sense to start with. Now that our calculation backed us up, I'm feeling pretty good about that. All right, so that wraps up lesson 1 of chapter 9 and lesson 1 of physics 30. Okay, so believe it or not, you are actually ready now. I mean, obviously not right now. You're probably going to go do some practice and some preparation and getting ready, do your assigned practice problems and all that. But that actually covers the material that is on the first topic quiz. Okay, so you're ready to write the first topic quiz once you've practiced this stuff, asked me some questions that you needed to go over and all that usual learning stuff, okay? But once you've done that, you can write the first topic quiz, which just covers momentum and impulse. You'll find that posted in the agenda as well as the Google Classroom. All right,